Okay, before I pick up where I stopped in the first video, I noticed that sometimes I was out of the screen on some of these things. So let's go back and take a quick screenshot of the stuff we've done so far. Now this was page 1. So if you missed any of that, go back and fill that in. This was page 2. And again, if you missed that, and I think I lost part of this when I was working on it. Okay, this is the bottom. And this was that. On this side, I think I lost a little corner here. So pick that up. And then I lost my little diagram here. I think I cut it off right in the center there. Okay. And now this is where we stopped. I'll try to be more careful on that in the future. Now, the only thing we did is we took the magnitude of V here and we wrote it in this, it sounded really component form, but we wrote it in these components here. It's I, which is along the, let's go back and look at that. That's this horizontal direction here. Cut it off again. And J, that's the vertical. Horizontal cosine, sine is vertical. And now we're just going to plug this in. Well, the cosine of 0 is 1, so this becomes 5 times 1i. The sine of 0 is 0, so this becomes 0 times j. And when we distribute the 5 across, we get 5i plus 0j. Now we don't have to write 0, so we can just write this as 5i. Okay, now these will be done the same way here. Now, let's do F. I was going to do B and C, but B and C are done the same way. The only thing is you're not going to get a 0 component back here. The sine of 30 degrees is 1/2, so you get 1/2 in the back. And same thing for 120 here. You can work that one out. Sine will be square root of 3 over 2, and the cosine will be 1/2. Now, here we're not given an angle. We're just told the direction of negative 3i and 4j. Now, the way we're going to do that is we're going to use the tangent of theta is equal to 4 divided by negative 3. Okay? This is y over x. Sine over cosine is what tangent is. But we need the angle. So theta is going to be the inverse tangent of 4 over negative 3. And for that, we're going to use the calculator. So now this is going to be an approximation. I'm going to reset it. Second plus 7, 1, 2. Now, for the most part, I'm working with degrees, although this would not make a whole lot of difference here. But let's go down and change this to degrees. Now I'm going to do the inverse tangent of 4 divided by negative 3. And I get negative 53 degrees. Now I rounded that, so. And I'm told my magnitude is 2. This becomes 2i cosine of negative 53 degrees plus j sine of negative 53 degrees. So let's put that in. Cosine of negative 53 degrees is 0.6. So this becomes 2.6 I plus sine of negative 53 degrees, which is j, and I'm going to round this to 0.8. And I'm multiplying all of that times 2. So this turns out to be 1.2i minus 1.6j. And we're done. Okay, take a look at that. Now let's talk about some word problems. So read all of this. And you can see this is where that inverse tangent comes from here. So I'm going to work a couple of these. I'm going to do example 8. Now, example 8 says you're pushing a heavy desk by applying a force of 150 pounds at 25 degrees to the desk. How much force is actually used in pushing the desk? What would happen if I increase the angle to 35 degrees? Now, I'm going to sketch this. So I'm going to make this my desk here. And notice I centered it at the origin. Now this says you're pushing it, but change that to pulling. It makes it a little easier for the diagram. So if this is 25 degrees, you're pulling in that way. And this magnitude, this is a vector, so that's 150 pounds. And this angle here at the origin is going to be 25 degrees. And how much force is used in pushing the desk? In this case, pulling the desk. So I'm only concerned about this horizontal component because I'm pushing it. The y component is lifting it. So I only want that component there. So I'm going to take 150, that's my magnitude, times the cosine of 25 degrees. And that will tell me this horizontal component going in this direction here. Okay. Now again, the other component going up is actually lifting the desk a little bit, so I don't really want that. I want this one. So I'm going to take 150 times the cosine of 25 degrees, and I see I've got 135, therefore 135.95 pounds. That's a force. I guess we could call it pounds. Now if I increase that to 35 degrees, I will have 150 times the cosine of 35 degrees, and I get 150 cosine 35 degrees, 122.87 pounds. And we're done. You can see the angle makes a difference here. Now, why do we have more force in this one than we do here? Well, if you think about it, how close are we to this angle, to the zero angle between the x-axis and that? Well, 25 is closer than 35 degrees. Now, if we'd been at zero, we would have had the entire 150 pounds. So as we go up, we reduce that. And the further up we go, the more we reduce it. Okay, that's the idea behind that. Okay, I was going to work number 10, but it's done the same way. Now, dot product. Now, a dot product is a scalar. It is no longer a vector. And to get a dot product, you multiply the corresponding components. For example, well, they just wrote this as u squared. They should have written it as u dot u dot v squared. Although squaring a vector means you almost have to take the dot product. But let's do b here. U is going to be 2, negative 2, and we're going to find the dot product of this with 2v. Well, 2v is going to be 10 and 16. So we get the dot product by taking 2 times 10 plus negative 2 times 16. Well, this is 20. This is negative 32. So the dot product of this is going to be negative 12. It's pretty straightforward. Now the other thing we want to talk about is the angle between two vectors. And we use this formula here. Okay, it's the cosine of theta is equal to the dot product divided by the magnitude, the product of the magnitude of the two vectors. Now don't be confused, this is just a regular multiplication dot here because these two are scalars here. Those are vectors, so the dot in between the vector means dot product, this just means multiply. So we see that u dot v is going to be 3 times 4 plus negative 1 times 3. And we want the dot product of u. That's going to be 3 squared, which is 9. Negative 1 squared is 1. So this is going to be the square root of 10. This is going to be 16 plus 9 is 25, the square root of 25. So 3 times 4 is 12, minus 3, and the square root of 25 is 5, so this becomes 5 square roots of 10. So this is 9 over 5 square root of 10. Now that's the cosine of that angle there, but what we need is the angle itself. So we're going to do the theta is equal to the inverse cosine of 9 over 5 square roots of 10. So let's put this in. And we're going to have second cosine 9 divided by 5 square root of 10, space outside, close this one, close that one, and we get theta is approximately 55 degrees. Okay, now we need to talk about something else, orthogonal. Now, orthogonal just means perpendicular. It just means two vectors do this. One may go up like this, and the other one goes across like that. And they form a right angle here. Now, for vectors, we call that as being orthogonal. And we sometimes call it being normal. And then we fall back on the old terminology of perpendicular. We know that two vectors are orthogonal or normal or perpendicular if the dot product is 0. So if you do a dot product and you get 0, then you know they form a right angle like this. Okay. Next section is complex numbers. Now we're not going to go over that too much. We don't use this a lot in calculus, and that's what this entire summer course is designed to do, is get you ready for calculus in the fall. Now if we need this in calculus, I'll spend a few minutes going over it, but for now I'm not. And the trigonometric form of a complex number, we have talked a little bit about that, but not a lot. And again, if we need it, I'll go over it. I'll take this half a class or something and go over that. Multiplication and division of complex numbers. Leonard Euler did a lot of work on this. And he has got papers out of the yazoo on these types of things. You don't usually see this until you get to college, but if we need it next year, we'll go over it before we do any application with it. Same thing with complex numbers and roots of complex numbers. So we're going to skip that. Now, as I said, we're trying to squeeze 36 weeks of work into 6 weeks here, so we're not going to be able to cover everything we'd normally cover. We just have to make that up later if we need to. Now, your homework comes from this section here, page 11 through far did we go? I think we stopped at 15, 14 or 15. Okay, I'm going to stop that video here. We're going to do one more on polars, and then we are going to call it quits for this unit.